I'm going to start recording again. We left off looking at absorption, so AB, and we had looked at absorption from air to water, and now what we're looking at is from water to air. So a classic example is groundwater contamination. So for instance, you have groundwater contaminated with dry cleaning solvents, and you wish to remove those contaminants from the water to the air, and then do some sort of treatment from the air. Same mass balance that we had before. Again, the system is typically run, and is shown here, on a countercurrent flow. So I'm just going to go to the next slide. I've got the same set of equations. So we have the mass in, and that equals the mass out. We're assuming that we have no reaction. And here, again, we're looking at the mass of contaminant. Now, if we have no contaminant in our initial airstream, then, well, disappears. This term is zero. And if we assume that we have, so what we're assuming here is close to 100% efficiency. Okay, so basically, somewhere, typically your efficiency is going to be somewhere often 95 to 100%. So the mass leaving the airstream is much greater than the mass in the water stream. So we've transferred the vast majority of that contaminant from the water, from that contaminated groundwater, to the airstream. Now, if we look back, okay, and we're looking at the airstream, so we have QA out, and we have QW in, and then we have QW out, and I just wrote this backwards, QA in. Okay, so we said that this term QA, the concentration in that, is essentially zero. Since we have a equilibrium between the sorry, the in this case trichloroethylene in the air leaving and in the water, we can write this mass equation balance in terms of a Henry's constant. So we're assuming equilibrium. We can assume we're assuming dilute solutions. We can use the Henry's constant, and what we can determine then is what we refer to as a stripping factor, that is a function of the chemical that we're removing and the flow rates in the air and water stream. So we have a property of the contaminant, and we have a design parameter. And from that, we can determine the number of transfer units, and we can also determine a height of the transfer unit. So what we need, okay, are the number of transfer units and the height of the transfer unit. We can determine as then the number of transfer units is a function of this stripping factor, it's a function of the removal efficiency, and the height of the transfer unit is a function of our liquid loading rate and the mass transfer rate constant. So that's really a function both of the chemical you're removing and the efficiency of that remove of the unit that you're using. So we can look at this example, and this is where we left off, is we have an example where what we're looking at is removing CO2 from water. So for instance, this could be in a water treatment system. Groundwater is often has high concentrations of CO2. And for instance, if we're trying to remove the hardness, soften that water, we may wish to remove CO2 before we begin the chemical softening process. So we have an initial CO2 concentration. Sorry, CO2. Yep. So initial CO2 concentration of 60 milligrams per liter, and we're desired concentration, the effluent, is 10 milligrams per liter. We are operating at 20 degrees C, 1 atmosphere. You are given a dimensionless Henry's constant for CO2, and that is your Henry's constant divided by RT, so it's adjusted for temperature. You're told the air-water ratio. You're given the loading factor for water, so that's the L. You have a Henry's constant. This is from the manufacturer. And you're told that the incoming air is free of CO2. So let's insert a slide. So we're told the influent CO2 is 60 milligrams per liter. The desired effluent concentration is 10 milligrams per liter. We are given a Henry's constant, and that's the dimensionless Henry's constant, and that is 0.8317. And so we can determine the stripping factor, and that is H prime times QA over QW. And we're told that that ratio is 160. So that is 8317 times 160, which is 133. Okay, so that ratio was specified in the problem statement. The number of transfer units is then 133 over 133 minus 1 ln. And because this is a ratio, we can leave our concentrations in milligrams per liter. We have 133 minus 1 plus 1 all over 133. And that is equal to 1.8. So the number of transfer units is 1.8. Sorry, that ratio is equal to 1.8. So R sub S over R sub S1. Oh, so it is equal to 1.8. I'm sorry. This is just, I'm rewriting the equation. Let me just rewrite that for you. So I've just written the equation. I wrote it backwards, so the height of the transfer unit is equal to L over MW at KLA. So our loading rate divided by the molecular weight of water. divided, times the, that's actually not the molecular weight, it's the density of water, the molar density. So this is our molar density of water, and our loading rate, and this is in kilomoles per second, and it's per meter squared. So it's per cross-sectional area divided by the molar density of water times KLA, and that's inverse hours. We have hours here and seconds there, so we need to convert. And that is 0.52. And I'm just going to add another slide so that we have space. Okay, and we said that NTU is equal to 1.8. The HTU we calculated as 0.52. So the height of our unit that we need is the height of the transfer unit times the number of transfer units. That is 0.52 over 1.8, and that is 0.93 meters. So we need a column about 1 meter high. That's much, much less than what we calculated previously for that previous example. I'm just showing you that it's relatively easy to remove a sufficient amount of CO2 from this aqueous stream in order to produce a water that could be efficiently softened using chemical softening. So we will end there. If there's any questions on absorption, so AB, this is, let me know. Otherwise, we will move on to absorption. Okay, I'm going to switch slides. And we're now looking at adsorption. So before we were looking at absorption, we're now looking at adsorption. The difference is with absorption, you can think of that as a three-dimensional process. And there you're looking at either dissolving a gas from the air into water or removing a gas that's in solution from the water to a gas phase. With adsorption, we're looking at transferring either a gas or it can be a liquid contaminant onto a solid support. So it's really, you can think of it more as a two-dimensional process because the reaction adsorption is actually occurring on a surface. So it's a surface phenomena. We talk about a adsorbate. So for instance, going back and looking at the previous example where we had, and we had a groundwater contaminated with trichloroethylene. It's in the groundwater. We could use an absorption process to transfer the TCE to the air. So now we have TCE in the air. We could then take that airstream and now we put it through a adsorbent. Okay, the TCE is your adsorbate, what's being sorbed, and that is being held. We'll talk about those forces, but it's being held onto a solid support or your adsorbent. These forces that hold that these chemicals can either be physical, so there's your electrostatic or van der Waals forces. We'll talk a little bit more about this later. Or they can be chemical, so they could be covalent or hydrogen bonding. And in the cases typically of physical attraction, then those reactions are reversible. Sorbents can be activated carbon, used extensively both in water treatment and in air treatment. Silica, alumina, a variety of materials that can be used as sorbents. They can even be your curtains in your living room. Somebody comes visiting, you let them have a cigarette in the house, and then after they leave, you smell the cigarette smoke in the living room. What's happened? It's sorbed. Those chemicals in that cigarette smoke have sorbed onto the fabric. So they're actually held there by some physical forces, typically, and the fabric itself acts as the sorbent. Now, these reactions, okay, and these sorbents are actually very effective because of the large surface area. And we look here, typical activated carbon has a surface area of about 600 to 1600 meters squared per gram. Okay, gram, just to think about it, if you have a little packet of sugar, that's about 2 to 3 grams. So it's not a lot of material, yet the surface area is somewhere between 600 to 1600. Activated alumina, not as high, neither are zeolites, and then you can produce synthetic polymers that have a similarly high surface area. And just to give you a kind of comparison, a size 5 soccer ball has a surface area of 3.3 times 10 to the minus 3 meters squared per gram. Okay, so we're talking in some cases 5 orders of magnitude greater surface area than the surface area on that soccer ball. Now, when we talk about these adsorption reactions, we talk about that the molecule that we're trying to remove is initially in the bulk phase. So we can mix that solution, and that's either the air or the water, in order to ensure that those molecules, for instance, let's take the TCE, come in contact with the sorbent. Now, once that, here's my molecule of TCE. That molecule initially enters what we refer to as the macropores. So these are the pores close to the surface. That particle then can diffuse into the pore structure, and most of the surface area is actually in the pore structure. So activated carbon may not look porous, but it actually is extremely porous. And these particles move, or these contaminants move into the pore space by diffusion. And they can eventually reach what we refer to as the micropores. We have the macropores towards the surface. Those pores get smaller and smaller in size, but most of its surface area is within the pore structure. The contaminant is actually moving by diffusion. Once the contaminant reaches a surface site where it can attach, then it attaches to that surface site. So for the most case, the rate limiting step is diffusion, not the actual absorption process where it adheres to that site. Now, sorbents can be non-regenerative. For instance, if you were to pull your furnace filter, talk about HEPA filters, you may also find that that furnace has a filter has activated carbon as a sorbent, so it can remove odors. Often, these non-regenerative systems, as you can see here, have multiple panels or multiple layers, and the air flows through those multiple layers. The mask that I've shown you is a mask with activated carbon present on the filter material or incorporated into the filter material. So again, you've got this porous support, and then you've got activated carbon on that support. So not only would that remove particulates, but it would also remove odorous compounds that could be a problem and can then be removed. They adsorb, okay, or attach to the activated carbon in the filter. Cigarette filters have activated carbon in there. Again, what it's trying to do there is remove tarous nicotine from the polychlorinated aromatic hydrocarbons that are potentially or are carcinogens. I'm just going to see if I can. We can also have non-regenerative systems that are installed in industrial settings. So in this case, we have some sort of a process. We may have a fume hood. We have a fan that's drawing air from that fume hood. We may have particulate removal. And then following that, we've got some sort of a non-regenerative carbon bed. So we have an activated carbon system here. And when that carbon system is what we call exhausted, so basically it can effectively remove more of whatever contaminants we're trying to remove, then we would remove that and replace it with typically a new cartridge, and that clean air is exhausted to the atmosphere. So we don't attempt to on-site do any sort of regeneration of that carbon in that cartridge. It's simply just replaced with a new cartridge, and then perhaps sent back to a company where they could do a bulk regeneration of multiple cartridge materials. We also have regenerative systems. These are often used where the product is valuable. So for instance, in dry cleaning industry, we may want to recover tetrachloroethylene, which is used, or perchloroethylene, which has been used extensively. So what we can do is we operate this typically with multiple beds. So we have some sort of a carbon adsorption system. So we're removing that perchloroethylene from the air stream. It sorbs onto the carbon. And then when that carbon is exhausted, we would switch to a different adsorption bed. And then what we do is we use steam, so we're using temperature. We're purging the contaminants from the bed using high temperature. Adsorption is an exothermic process. So it's exothermal. So that means that if we increase the temperature, we will decrease the extent of adsorption. So by doing this, we can shift that equilibrium to desorb the perchloroethylene from the activated carbon and then collect that and reuse it. You can see that in this system here. So here we have a fan, we've got solvent-laden air. Often you'd have a particulate. In this case, you'd have a particulate matter filter, so you're removing the particulate matter. And then you're gonna have a heat exchanger. You wanna cool, if that gas stream is hot, you wanna cool that gas stream. Because as I said, adsorption is exothermic. So the higher the temperature, the lower the absorption that you can achieve. So typically, we want to achieve an air temperature somewhere between 15 to 40 degrees C. So we're going to lower the temperature here to somewhere between 15 to 20 degrees. We then remove those solvents. When we have exhausted the bed, the sorbent, then we can take that sorbent bed offline. We can regenerate with steam. We can recover the solvent vapor. Typically, we'll have some sort of condenser. We'll talk about condensers on Monday, so that we can recover the material. So as I mentioned, we have two different types of mechanisms. We have chemisorption and physical absorption. Chemisorption is a much stronger bond. So you can see here, typically we're looking at about 10 kilocalories per gram mole that's released, whereas only about 0.1 with physical adsorption. Your chemisorption occurs typically with covalent or hydrogen bonding. These are much stronger bonds. They're actually, because they're much stronger bonds, they're much more difficult to desorb those chemicals. Which also means that recovering that sorbate material is actually very, very difficult, if not impossible. On the other hand, physisorption, the molecules are held by either electrostatic interactions, dipolar interactions, weak van der Waals forces. So desorption is much easier, and you can use this to recover the adsorbate. Any sort of adsorption, when we look at that, we use what is referred to as adsorption isotherms. Isotherm just meaning same temperature. So what we do is, let's go back to our trichloroethylene. So for instance, so we have a solution that contains trichloroethylene, and all of them contain the same concentration of trichloroethylene to start with. We're going to add different masses of activated carbon. So let's say we start with let's say we have 100 micrograms per liter. That's our starting concentration. It's going to be the starting concentration in all. And let's say we have 1 liter of solution. And I'm just doing this with water. And in this case, let's say we add 3 grams of activated carbon. We're adding 5 grams of activated carbon. In this case, we are adding 7 grams of activated carbon. And the control contains no activated carbon. So what we're going to do is we're going to mix these. So all of them get mixed. Now we'll do the same thing with the control because we want to treat the control exactly as we treat our samples. We're going to mix these. We're going to allow them to reach equilibrium. And after it reaches equilibrium, we will measure the equilibrium concentration in each. So here we have our equilibrium concentration. We have our initial concentration. And we have the concentration of the solid. So that's 3 grams. I'm going to multiply everything by 1 liter because I've said that we have 1 liter solution. And what do we have? We have the mass sorbed or adsorbed over the mass of adsorbent. So this X over M or Q term is the mass of your sorbate that's sorbed divided by the mass of the sorbent. And each of these are determined at an equilibrium concentration. Now we have multiple models that are used. I'm not going to go into these in any great detail, but basically for very low concentrations, this X over M term is a function of the equilibrium concentration. So it's a linear function. Langmuir isotherm is more complicated. It's actually based on thermodynamics, and it assumes a monolayer coverage of your contaminant on the sorbate. And then the last one is a Freundlich isotherm, which assumes a power function. And the Freundlich isotherm is entirely empirical. Sorry, my allergies are acting up. So there's actually no theoretical basis for the Freundlich isotherm, although there is for the Langmuir. We can linearize each of these. And actually, we can linearize each of these. I'll skip that last slide, but what we've done is we've linearized these. For the Freundlich isotherm, because it's a power function, we'll use a log. So you can see we have the log of X over M over the log of C. We plot that, and what we've done is we've taken these, a function that looks like this, and we have linearized it. And what we can do then is tell which is the better or more effective sorbent. So for instance, if we need, let's change this here, we need to achieve a log C of so log 1. This carbon is our optimal carbon. If, on the other hand, we need to achieve a lower concentration, so 10 to the minus 2, this other carbon would be the better carbon to use. And we're also going to look at how cost effective is it. It may be that this other carbon, our red carbon, is much more costly than the yellow carbon. So it may make sense actually to use the yellow carbon because of the economics. We can also linearize a Langmuir isotherm. The way that we linearize that is we take 1 over X over M, and we're plotting 1 over C sub B. Okay, and notice here, our intercept is that term 1 over A, and the slope is 1 over AK. Similarly with our For inlet isotherm, we have a slope 1/n and a intercept of log k. So we can determine from the slope and the intercept, we can determine the parameters we need. So let's look at an example here. Okay, so we have a dry cleaning process, and it is exhausting 1,500 standard cubic feet per minute. So the standard cubic feet in the US is typically 59 degrees Fahrenheit or 15 degrees C and 1 atmosphere. The airstream contains 680 parts per million of carbon tetrachloride, or PERC. And we are going to, and let me change this back. I'm just going to change it because they give you standard, and we're just going to change this here to, if I can. Okay, we're going to change this here, and we're just going to use 59 degrees Fahrenheit and 14.7 psi. So we'll just adjust that, and we'll use 59. So what we want to do is we want to estimate the amount of carbon that is required to operate on a 4-hour cycle. That means that what we would do is we would stop the system every 4 hours, and we would regenerate and recover that PERC. The molecular weight of carbon tetrachloride, like I said, PERC, it's carbon tetrachloride. It's not the same thing. So we're looking at carbon tetrachloride, and we're going to use a working capacity of 25% of the saturation capacity. So we're assuming that the actual capacity we're going to operate at is 25% of the saturation capacity. So the first thing we need to determine is the mole fraction of carbon tetrachloride. Okay, and we said it was 680 parts per million, and that is 0.00068. Okay, so that's the mole fraction. That's also the percent volume. We looked at that at the beginning of the semester. So the partial pressure of carbon tet is equal to the mole fraction times the total pressure, and that is 0.00068 times 14.7 psi, okay, and that is 0.010 psi. Okay. We need to determine the capacity of the carbon for carbon tet, and we can use this figure here, and all the figures are all from the EPA student manual that is posted on LONCAPA in your reading. So we have 0.01, we read up and across, and that is roughly 45%. So that means that 45 pounds of carbon tet can be sorbed onto 100 pounds of carbon. Okay. Or 45 kilograms of carbon tet sorbed onto 100 kilograms. So that's the 40, this is from that 45%. Let's add the slide in here, and the flow of carbon tet is equal to 1,500 cubic feet per minute, that was given, times 0.00068, and that is equal to 10.2 feet cubed per minute. Okay, so that's the flow rate. The 15,000 cubic feet per minute is the flow rate of the air, but it contains 680 parts per million of carbon TAD. So we have 10.2 cubic feet per minute carbon TAD. The density, or molar density of air is 1 pound mole of air occupies 379.4 cubic feet. We have 154 pound mass, molecular weight, times pound mole of carbon TAD. So we're multiplying by the molecular weight. And we need this on an hour basis, so we'll multiply by 60 minutes per hour. And that means that we can absorb about 250 pounds of carbon TAD per hour. Now we said we wanted to use a 4-hour cycle. So we have 4 hours. So you can think of really this in terms of applying what we are applying to this carbon and what we're sorbing onto it, or what we're really sorbing onto it is 993.7, about almost 1,000 pound mass over that 4-hour period. So that's what we'll, okay. And so this is what it's actually, so that's how much carbon TAD we need to sorb in that 4-hour time period. Okay. So the amount of activated carbon, so this is the amount of carbon TAD that we need to sorb. Okay, so that's what we need to sorb. The amount of activated carbon needed, okay. We have 9. This is the carbon TAD. We can sorb 45 pounds of carbon TAD for every 100 pounds of activated carbon. So we need roughly 2,200 pounds of activated carbon. But we said that the working capacity is 25% of the saturation capacity. So my working capacity, and this was given, is 25% of the saturation capacities. We're not going to operate to complete saturation. So we have the 2,200 pounds, divide that by 0.25, and we need about 8,800 pound mass of activated carbon. And then what we would do is we would regenerate that every 4 hours. We'd have a second reactor if we need to operate this continuously, then we would have a second reactor, and that airstream would go to that second reactor while we're regenerating the first one, and we would just continuously switch back and forth. That airstream that we collected would then, we'll talk about on Monday, we'll talk about condensers. So then what we would do is the airstream would go into a condenser. We can condense that, in this case carbon tet, and then could reuse it. I'm going to stop there. We'll finish adsorption on Monday, and we'll look at condensers. The last thing we'll look at on Wednesday is incineration, and that should pretty much finish it. What I planned on covering. So if there's any questions in the last couple of minutes, happy to answer those. No questions? Okay, so we will end there. And we've got one other problem related really to the FE exam. It's the type of problem that they you might see in the FE, and we'll do that problem on Monday, and we will look at condensers. So, or what is, sorry, on Friday. Why am I thinking it's Friday? It's Wednesday. We'll finish this on Wednesday. We will have class on Friday. So until Friday, have a good day.